们准时开始我们此次这个中瑞零碳研讨会。那么各位专家、各位来宾，大家下午好，我是中国建筑科学研究院的杨新妍。首先呢，非常欢迎您参加中瑞零碳建筑系列研讨会。那么今天呢是本次研讨会的第7期，主题为这个水泥行业去碳化和创新水泥材料 LC3。那么本次呢，我们是采用了这个中英同声传译的方式进行。如果大家是从这个 Zoom 链接进来的，然后可以从这个最下面有一个小地球的图标。您在那儿可以选择这个合适的语言。如果您是从这个直播的平台进入我们的论坛呢，您可以选择中文频道、英文频道，对这个语言呢进行一个选择。那么我们这次研讨会的举办呢，在此呢非常感谢瑞士发展合作署、中华人民共和国住房和城乡建设部、瑞士绿色建筑协会的大力支持。本次研讨会呢，我们非常高兴请到了2位演讲嘉宾，一位是中方演讲嘉宾，浙江大学建筑工程学院建筑材料研究所的副教授孟涛博士。那他呢也是中国硅酸盐学会建筑固体废弃物特别委员会的副秘书长，那么主要从事建筑废弃物处置和循环利用及先进水泥基材料结构和性能的研究。那么另外一位演讲嘉宾呢，就是来自洛桑联邦理工学院材料实验室的负责人 Karen Scrivener 教授。那么他的工作重点呢是改进水泥基材料及其应用。那么他还担任 LC3 项目的主任，并且是关于水泥的研究和创新网络一个叫做 NanoSim 的这个研究网络的创始人。那么呢，我们首先非常高兴先邀请浙江大学的孟涛教授，为大家做报告。如果您有任何问题，欢迎您呢，就是不管是在 Zoom 链接还是从这个直播链接平台进来，您都可以将问题呢写在聊天框内，然后我们稍后呢会汇总大家的问题来进行讨论。那么首先先有请孟教授，孟老师您好请分享，谢谢。
好，谢谢主持人，各位同仁。我是浙江大学孟涛，首先非常感谢主办单位邀请我参加本次中瑞零碳建筑研讨会。那么大家都知道，零碳建筑和低碳材料或者零碳材料的研究和应用有着密切的联系，因此我的报告也将面向水泥混凝土这种应用最广泛、应用量也最大的工程材料，介绍中国水泥混凝土低碳技术的研究进展。其中不少是我们浙江大学低碳研究团队近些年来的研究成果。那么我的报告，我的介绍分为4个部分。首先呢是中国和建设行业碳排放的一个情况，然后呢是从胶凝材料和混凝土角度分别进行低碳技术的介绍，最后呢是一个总体的一个结论。我们可以看到，左图是显示了近10年于第2次工业革命前期全球温度的一个变化情况。可以看到全球的温度平均增加了 1.2 度，部分地区平均温度增加值是超过了4摄氏度。因此这些年右图显示的干旱、暴风、洪水、寒潮、酷暑等极端气候也是频繁出现，这主要原因被认为是人类使用矿物燃料排放出大量的二氧化碳等温室气体，从而产生了一个温室效应，导致全球的变暖。如何控制大气中的温室气体浓度已经成为国际上的关注的焦点。中国在2020年提出2030年碳达峰、2060年碳中和的双碳目标，这体现出一个大国的一个责任。这里的话显示了全球各主要国家历史上和当前的碳排放的一个情况。第1次工业革命以来，美国、英国、欧盟等发达国家碳排放总量超过了全球的1半以上，而中国由于人口基数大、经济发展快，造成碳排放量的不断增加。当前 占全球碳排放总量的31%。但是从右下角的这个图，我们可以看到，中国人均碳排放量还不到美国的一半，而且从2000年到2020年的人均碳排放量增长值也小于美国。那么同时，欧洲和日本很早就开始研究和推广各类碳减排技术，因此2000年到2020年人均碳排放值的增长值是非常小的，这的确值得中国去学习和借鉴。下面我们看一下土建行业的一个碳排放的一个情况。2019年全球碳排放量，建筑业的碳排放量占到全球碳排放总量的39%，其中11%来自于建筑材料和建造，28%来自于结构的服役和运营。同样是2019年，我们看到右图，中国建筑业碳排放量占到碳排放总量的51%，这远高于全球的一个平均水平。其中建筑材料和建造占29%，是全球平均水平的2.6倍。当然，这原因不仅显示中国新建工程较多这样一个原因，同时也暗示着我国建筑材料制备过程中碳排放的二氧化碳比例比较高，因此土建行业碳减排的工作对于中国双碳目标的顺利实现是显得非常的重要的。这张图则是显示了中国建筑业碳排放的组成情况。我们可以看到，建筑材料占比是达到了55%，其中钢材27%，水泥23%。建筑材料的所占的比例超过了服役运营和建造加起来的所有的比例，所以这表明建筑材料在整个中国建筑业碳排放的这样一个总量是非常的大的。那么其中水泥又占到建筑业碳排放总量的23%，因此水泥混凝土碳减排技术的研究和应用则有着极为重要的一个价值。第二部分是低碳的胶泥材料的一个技术。这张图则是显示了建筑物、混凝土和水泥的总的一个碳排放的一个构成情况。我们可以看到，混凝土的碳排放占到了整个建筑物的38%。那么这个38%呢，主要是来源于原材料的制备以及搅拌、运输、浇筑等施工的一些的步骤。而水泥的碳排放量又占到了整个混凝土碳排放量的70%以上。水泥碳排放组成中最大的2个部分就是石灰石的分解和煤的燃烧。因此，低碳胶泥材料技术的关键就是在于硅酸盐水泥要减少石灰石的用量，以及研发低温煅烧条件下的新型胶泥材料。这张图则显示，为了减少石灰石分解产生的碳排放，我们一个常用的方法就是采用粉煤灰、矿渣等矿物质材料替代一部分的水泥熟料。如果参入15%的矿物质材料，就可降低整个水泥碳排放量的10%到30%左右。在这里的话呢，我们介绍浙江大学低碳团队的2个研究成果。一呢是发现20%的废旧陶瓷粉代替水泥后，不仅可显著增加基体和界面过渡区的密实度，提升混凝土的后期强度，而且使得 C40 混凝土价格下降11%，总的能源消耗下降7%。我们具体可以看到中间的几张图的这个结果。二是发现纳米碳酸钙能显著增强粉煤灰的火山灰活性，从而大幅提高粉煤灰的参量，这有助于进一步减少水泥的一个碳排放量。我们可以看一下右边的几张图的这个结果。 从这一页开始，我将依次介绍3种新型的低碳胶凝材料。首先呢是 LC3 低碳的水泥。那么 LC3 低碳水泥，它是通过对高岭土进行800摄氏度的悬浮和回转煅烧活化，以及低温改性后制备出来的一个石灰石煅烧粘土水泥。那么与传统的硅酸盐水泥相比，它可以降低熟料的用量50%以上，同时降低二氧化碳的排放量约40%以上，最大可到50%。那目前 LC3 水泥在瑞士、巴西、印度正在逐步的推广。近5年的话呢，中国也开始关注这种低碳胶凝材料。右图则显示中国学者在对 LC3 水泥流动特性和水化进程的相关的研究。中间的图呢，则是中国学者将 LC3 水泥用于混凝土结构和膨胀土基层方面的一些的研究成果。第2种低碳胶凝材料的话呢，是镁系的胶凝材料，它的原材料主要为煅烧氧化镁。相比于石灰石分解，这不仅可以大幅降低制备过程中的碳排放量，而且镁系胶凝材料在服役过程中还会不断吸收空气中的二氧化碳。部分研究表明，这是一种零碳甚至是负碳胶凝材料的一种技术路径。那么在中国，重庆大学等高校开展了系统的磷酸镁水泥的研究。我们团队也尝试用纳米材料提高氧化镁的水化反应程度，从而改善其各项技术性能。具体可以见右边的这相关的一些的。LC3 低碳水泥，它是通过对高岭土进行800摄氏度悬浮和回转煅烧活化与低温改性后制备得到的石灰石煅烧粘土水泥。与传统的硅酸盐水泥相比，可以降低熟料用量50%以上，降低二氧化碳排放量约40%，最大可到50%。目前在瑞士、巴西、印度正在逐步的推广。近5年，中国也开始关注这种低碳胶凝材料。右图中显示中国学者在 LC3 水泥流动特性、水化进程以及混凝土结构和膨胀土基层方面的研究成果。请翻一下页。第2种低碳胶凝材料是镁系胶凝材料，它的主要原材料为煅烧氧化镁。相比于石灰石分解，这方法不仅可以大幅降低制备过程中的碳排放量，而且镁系胶凝材料服役过程中还会不断吸收空气中的二氧化碳。部分研究表明，这是一种零碳或者是负碳胶凝材料的技术路径。在中国重庆大学等开展了系统的磷酸镁水泥研究，我们团队也尝试用纳米材料提高氧化镁的水化反应程度，改善其各项技术性能。好，第3种低碳胶凝材料是地聚合物。地聚合物主要原材料为偏高岭土粉煤灰或矿粉等含硅和铝的物质，通过强碱的激发，促使活性硅和铝发生反应，生成硅铝酸盐产物，起到交接材料的作用。因为碱激发这种胶凝材料不需要高温的煅烧，所以相比于传统的硅酸盐水泥，地聚合物这种碱激发胶凝材料的碳排放可减少40%。我们团队制备了偏高岭土基和赤泥基的地聚合物，并通过掺入微钠纤维和纳米晶合作用，进一步改善地聚合物的强度特性。其中，纳米改性赤泥地聚合物抗压强度超过了60兆帕。好，除了添加矿物质材料以及研发低碳胶凝材料外，通过补给水泥生产中排放的二氧化碳，用于碳矿化胶凝材料和骨料的制备，也是水泥低碳技术的重要手段。左图则显示了水泥行业碳补给后再利用的这个过程。右图显示可以通过碳矿化钢渣、电石渣、粉煤灰、磷石膏等含有丰富钙镁碱性组分的大宗固废制备出人造骨料。此外，混凝土再生骨料 也可以通过碳矿化技术实现强化，并进一步降低水泥混凝土的碳排放。碳养护水泥制品是另一项可以显著减碳的技术。这项技术利用水泥水化产物与二氧化碳反应生成碳酸钙等物质，显著提高水泥制品的力学性能，特别是早期性能。我们团队与浙江大学能源学院合作，在河南强耐新材股份有限公司建成二氧化碳矿化养护制备建材示范生产线，每年封存利用二氧化碳可达5万吨，消耗固废60万吨。在浙能集团兰溪电厂开展了二氧化碳补给与矿化利用示范，补给能力达到了1.5万吨每年。第三部分为低碳混凝土技术。我们团队正在浙江省兼并攻关研发计划的支持下，进行 carbon mix 的研究，直接将二氧化碳拌合进入预拌混凝土或混凝土构件中，并解决了混凝土直接水合碳化过程中闪凝、强度下降以及二氧化碳拌合量低等问题。相比于加拿大 CarbonCure 公司的研究成果，碳拌合量从水泥用量的 0.3% 增加到 2.67%， 且混凝土流动性和抗压强度几乎不变。目前我们团队正和浙江省建材集团在德清开展 Carbon Mix 的工程应用。右下图显示了固碳混凝土项目中碳补给、运输以及加注和拌合流程及其相关的设备。低碳建造是低碳混凝土技术的重要组成部分。虽然建造本身占碳排放总量所占比例不高，前面说过只是 2%， 可是低碳建造技术减碳效果却是远大于 2% 的。研究表明，与传统建筑相比，装配式建筑可减少碳排放量 15% 左右。这主要是因为一是规模化、集约化的生产能够节约材料的用量，降低生产的能耗，并减少建筑废弃物的产量；二是机械化安装也可降低建筑施工过程中的噪音以及废物、废水、废气等排放的污染。3D 打印混凝土是通过人工智能建造施工方式制备混凝土材料和结构，可以现场进行原位的 3D 打印，也可以利用装配式理念在工厂进行预制 ，3D 打印后再到现场安装。相比于传统混凝土制备和施工方式， 3D 打印混凝土可以减少碳排放量约 5% 左右。下面我们要着重讲一下这个建筑固废的循环利用。实际上，建筑固废循环利用它也具有巨大的低碳的效益。具体在以下的4点：第一，再生材料是可以减少原生材料的使用量。那么，按照现在最新的规范，再生材料的碳排放可以按照原生材料的 50% 来计算。第二个，建筑固废就地循环利用，可以大幅降低材料运输过程中的碳排放。再次是建筑固废中的一些的再生的粉料，我们可以将它进一步制备成高活性的矿物掺合料，部分替代水泥，从而减少整个碳排放。最后的话是再生骨料的碳化强化，也可以实现相应的碳汇的效应。这是我们建筑固废循环利用减碳机制的主要的几个减碳机制。好的，那我们团队开展了近15年的建筑废弃物的循环利用研究。那我们的特色呢是希望实现建筑固废的全利用，这不仅包括原材料中间废弃混凝土、废砖、废瓷砖等全面的全利用，而且包括再生材料中粗细骨料和粉料的全利用。右图则显示了我们针对拆除垃圾全利用制备出矿物掺合料、墙板以及道路基层等方面的一些研究工作。 下面首先讲一下再生粉的一个利用。我们知道，如果再生骨料中混有大量粉料，会严重影响其技术性能。我们团队发现，除层粉和筛分粉这两种再生粉料的主要矿物组分与粉煤灰很相似，并且通过复合激发的方法实现了再生矿物掺合料的制备。结果发现，机械力化学活化后，再生矿物掺合料活性指数可高达 0.90， 远超粉煤灰 0.70 的技术要求。目前研发的再生掺合料可以替换 30% 的水泥，是一种非常有潜力的一种辅助胶凝材料。同时，我们团队还通过废弃粘土砖粉制备了地聚合物胶凝材料，并且将它用于透水混凝土中。相比于传统硅酸盐水泥天然骨料的透水混凝土，当焦骨比均为 0.15 的时候，单方透水混凝土成本可节约81元，碳排放降低90公斤。因此，用废弃粘土砖制备地聚合物胶凝材料是具有显著的经济效益和环境效益。我们团队还进行了全再生结构的研究和应用，针对再生粗细骨料研究了取代率为 100% 的时候，全再生砖混骨料混凝土构建的静力和长期性能，并在舟山建成了全再生混凝土房屋结构。目前该结构正在持续的监测之中。事实上，相比于天然材料，各类再生材料的性能均存在劣化的现象。因此，提高再生材料技术性能是建筑废弃物高质化利用的关键。我们团队已形成了再生骨料的纳米强化、微生物改性、碳化和动容改性等多项技术，改善了再生材料的构性特征，显著提高其吸水率、压碎指标值等再生材料以及抗压抗折强度、钢筋锈蚀等再生构件的主要性能指标，解决了再生材料高等级利用的技术难题。在建筑固废处置技术的研发过程中，我们团队逐渐形成了全组分高效利用与固碳技术的协同处置思路，实现了减碳和固碳的双重效益，并高质化应用于建筑、海洋、交通等工程领域。近期我们正在开展全再生固碳混凝土在海洋牧场中的应用研究，希望能够实现产品技术性能和生物适应性的提升，产品的成本降低，以及固废利用和固碳增汇等综合的效益。以下是几点结论：一是先进胶凝材料将引领水泥混凝土低碳技术的发展，但是当前矿物质材料的替代仍然起到特别重要的作用。二是低碳水泥和低碳混凝土技术有着紧密的联系，部分技术可通用于水泥或混凝土。三是对于低碳水泥混凝土乃至于低碳建设、建筑废弃物的循环利用将发挥越来越重要的作用。OK， 我们团队目前包括建筑材料和结构工程方向共6位老师。本次的报告也汇集了各位老师近期的研究的一个成果。好， 以上是我的汇报，谢谢各位同仁的聆听和关注。
好的，那么我们感谢孟老师的那个介绍。那么我们根据议程，接下来有请洛桑联邦理工学院 Karen Scrivener 教授为大家做报告。那么教授报告结束后呢，就是我们的这个讨论和这个问答的环节。如果您在这个过程中呢有任何的问题，欢迎您发到这个对话框中，我们会收集问题，稍后为您解答。谢谢。Please, Karen Scrivener, Professor Scrivener, please.
Okay, so I hope you can see my screen okay. Thank you for this opportunity to present the LC3 technology. And what is particularly interesting about this technology is that it's really available now, and it can be implemented fast and at full scale all around the world. And this is in contrast to many other ideas which are really much more hypothetical. So I think the main message I want to give you is there's no magic bullet solution. We hear like magnesium cements can be carbon negative, but these are very far from application. Maybe this will be in 50 years' time. And really what we need to focus on is what we can do today. There are many solutions. And if we combine them all together, we can achieve massive reductions. Now, we can't do without cement because this is really making up more than all other materials put together. And it's only for this reason that it accounts for such a high amount of CO2 emissions. If you look at this graph here on the top right, you see that if we look at CO2 in terms of CO2 per kilogram, the products that are based on cement are really the lowest of other materials. So we don't make things any better if we replace concrete with other materials. And we cannot do this because simply we just don't have other materials. So for example, people are claiming that timber is a very environmentally friendly material. This is true, but the problem is we don't have very much timber. All the timber we can use in the next 30 years is already in forests. And to replace just even 1/4 of materials based on cements with timber, we would need to plant a new forest 1.5 times the size of India. And clearly this would not be possible. Now, when we look at where the emissions of cement are coming from, it's important to realize that only about 40% is coming from the fuel. So this means even if we can have technologies that use renewable energy, this can only mitigate this 40%. 60% of the emissions are coming from the breakdown of limestone. Limestone is 80% of the raw material. And during the production of cement, limestone, which is calcium carbonate, is broken down to calcium oxide and CO2. So when people see this, they say to me, well, can we make a cement with a different chemistry? And the short answer to this is no, because we are limited by what we have available on Earth. Only 8 elements, which are oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium, make up 98% of the Earth's crust. So clearly we cannot base cements on anything which is in this remaining 2%. And then if we consider how cement works. So what happens when we mix cement with water? We have the gray powder, which is floating around in water. And what is happening is the cement is dissolving. So it's dissolving like sugar in your coffee. And then the elements are making new combinations, which are precipitating as hydrates, which I've shown here in red, which are like the glue that holds the whole cement together and gives it strength and durability. So these are the two essential things we need. We need dissolution and then precipitation. So if we look back at what are the most abundant elements on Earth, what we find is that the oxides of sodium, potassium are too soluble. So they don't precipitate hydrates. They don't give the glue to bind the cement together. On the other hand, the oxides of iron and magnesium are too insoluble. And this is really the problem of the claimed magnesium cements, that they cannot really work in the same way because the magnesium is very low solubility. And this means we come to the system of just 3 oxides, the calcium oxide, the silicon dioxide, and the alumina, where we can make cementitious materials. And this system is well known to scientists. It has been studied for more than 100 years. And in this system, we only have 2 regions where we have cement. We have this region here, which is calcium silicates, which we call Portland cement. We also have this region where we have calcium aluminates, calcium sulfur aluminate cements. And this second region has received a lot of attention because you need less calcium oxide, that means less limestone, and so less CO2. But unfortunately, we don't have minerals which contain much greater quantities of aluminium compared to silicon. We have things like bauxite, but this is very localized and it's really used for producing aluminium, which makes it expensive. But even if all the current bauxite production was diverted to these new materials, we could still only satisfy about 10 to 15% of current demand. And we see in China, these cements have been produced for more than 50 years, but today the production is less than 1/10% and is decreasing due to various problems like the raw materials. So here we see that Portland-based cements are an inevitable consequence of the chemistry and geology of the Earth. And therefore, blended cements are the most realistic option to reduce CO2 and extend resources. And also this is important because blended cements have already been used for many decades. For many decades, we have cements which are incorporating slag, which comes from producing iron, and fly ash, which comes from coal. However, today, the amount of slag and fly ash available worldwide is only about 15% of the demand for cement. And this amount will decrease in the future because the most important thing we have to do to avoid global warming is to stop burning coal. So fly ash in medium term will disappear, slag amounts will decrease. What other materials do we have? Well, we have a lot of limestone, which is already used as a substitute material, but we cannot substitute more than about 10% of this without losing the properties. And then when we look at other materials, people have worked on things like waste glass, vegetable ashes, but the amounts of these available are really in very short supply. The only thing we have which is available in the quantities required are clays, which can be calcined, that's to say heated in the range 800 degrees when they become very reactive materials. So in summary, there is no magic solution. Blended cements with supplementary cementitious materials would be the best solution for the future. The only material available in viable quantities is calcined clay. And what we discovered, which is behind this LC3 technology, is the synergetic reaction of calcined clay and limestone allows you to go to very high levels of substitution. And this is the essential idea behind the LC3 project, which we started in 2013 and has been supported for the last 8 years by the Swiss government through their Agency for Development and Cooperation. And LC3 simply identifies what are the ingredients we have in this cement. It stands for limestone calcined clay cement. So why does this have lower CO2 emissions? Well, in conventional Portland cement, we have about 95% clinker, which is emitting the CO2. In LC3, we have only 50% clinker. And in fact, we can go to even lower amounts in the long term. We have 30% calcined clay, which has a little bit of CO2 from the calcination process, but this is much, much lower than for clinker. And limestone has virtually no CO2, only a very small energy for grinding is needed. However, even at this level of substitution of 50%, we can have materials which can exceed the strength of the reference in only a few days. And this is in very sharp contrast to traditional SEMs like fly ash, where we may have to wait 90 days to recover the same strength as the reference. With LC3, we can do this in 3 to 7 days. So simply put, this is 50% less clinker, 40% or more less CO2 with similar strength and some properties like chloride resistance and resistance to alkali silica reaction are vastly improved. Now, the first question is to look at what kind of clays are suitable. We need to have a certain amount of this mineral kaolin. So this kaolin type clay is what's called a 1-to-1 clay, which means it has one layer of silicates and one layer of aluminates. And when it's calcined, that's to say heated to 800 degrees, this structure becomes disrupted and both the silica and alumina are available to react. Now, we don't need high-level metakaolin. This is very important because when people look at reserves, then they are talking about very high purity materials. We only need around 30 to 40% of this mineral kaolin. And the reserves of these kind of clays are many, many orders of magnitude higher than those for pure metakaolin, maybe 1,000 times or even more. And these are often wastes which are over or underburden, results of tailings from other mining operations, etc., which can be reused. So we have now tested more than 70 clays from around the world. We can measure the kaolin content quite easily by looking at this weight loss step in the range 400 to 600 degrees. And when we look at the strength development, we can see that this kaolin content is the overwhelming parameter controlling strength. So the other minerals which are present, like quartz or iron oxide, these do not influence the results at all. It's just the presence of the kaolin. And the red lines here indicate the reference strength of the Portland cement. So we can see that at 7 and 28 days, we only need about 40% kaolin content. And some of these clays, even with 30%, are really doing very well. Now, these kind of clays are very, very abundant. As I say, we only need 30 to 60%. If you have more, you can use more limestone. If you have less, you can enrich by separation. This is the distribution of kaolinitic clays. Everywhere we see this orangey yellow color, we will have very suitable clays. And we can see in China that this, certainly in the southern part, are very, very abundant. And even in areas which do not look so promising, like for example, in Egypt, where we have worked a lot, we have been able to find very good clays. So this color gives you a first indication, but there are also clays in many, many other places. This is very important. Now you can use these calcined clays in two ways. You have to find the clay, you have to process it, and then you have to calcine. And then you can either blend all the ingredients together, the calcined clay with the clinker, the limestone, and the gypsum, and this is what we call LC3. Or you can make an additive. You can add at the concrete level, where you intergrind the calcined clay, limestone, and gypsum, and then you add to OPC, and you're using concrete. And this slide just shows the same thing in another way. You either grind everything together to make LC3, or you take 1 bag of Portland cement and 1 bag of LC2 to make, again, the same composition. Now, for the calcination of the clay, what is very important is this can all be done with existing technologies. The loss of water occurs in this weight step between about 400 and 600, but we can really improve the reactivity by heating higher to the ideal range 700 to 850. So this is quite a wide window, which allows easy processing. And to do this processing, you can use rotary kiln, you can use flash calcination. Both have different advantages and disadvantages, but we see really very negligible impact on reactivity. And you can even adapt an existing clinker kiln. So we know in China you have a lot of old kilns. These can easily be adapted to calcining clay rather than having to be demolished, which is, of course, the waste of resources. We have even been able to make calcined clay in a clinker kiln only 6 hours after stopping production of clinker. But of course, in the long term, it's better to adapt the burner to have lower temperatures. So this is something we have really proved in a full scale. The first industrial production we made was in Cuba. And here we could make concrete blocks, which is a very commonly used building material. And these blocks could be produced in the factory in exactly the same way, with no need to retrain the workers in the factory. And the house was built of these concrete blocks, but also this render, which is applied to the outside. This was also made with LC3. And the masons who applied this render really appreciated the very nice cohesion and flow properties of the LC3. And then we started our work with partners in India. This is another demonstration house we built here. And we could calculate that this single house saved around 14 tons of CO2 compared to existing solutions. And now we are seeing many plants starting to produce calcined clays on a commercial basis. This is a plant that was built 2 years ago in Ivory Coast. And what is quite important in this plant was they could demonstrate at full scale the possibility to control the color of the clay. So many people know that clays often have a red color. This is coming from the iron oxide, which is also present in the clay. And with a very simple technology, which is coming from the brick industry, you can control this color to make a gray like people are more used to for cements. So just to talk briefly about some of the key advantages, we have much improvement of chloride resistance and total suppression of alkali silica reaction. So looking at the chloride resistance, this shows a comparison of different materials. The black line is the reference pure Portland cement. And you see after only 6 months, the chloride penetration is about 40 millimeters. When we have different blends with slag, this is improved, and blends with fly ash, this is improved still more. But by far the best performance we see with the blend of calcined clay and limestone, which is this purple, solid purple line here. And when we calculate the diffusion coefficient, we can see the diffusion coefficient is 10 times less than for the reference. So we have a 10 times improvement of performance. The workability may be an issue because clays are very fine, but good properties can be controlled by admixtures. And the admixtures can be the products which are already on the market. And many admixture manufacturers now are producing special admixtures for calcined clay blends, which work extremely well. In fact, you can have real advantages, particularly in self-compacting concrete. In self-compacting concrete, you need fluidity, but you also need good cohesion. And this good cohesion is brought by the clays, as you see here. Very good cohesion, no segregation. So what is the potential of this technology? This graph here shows the average level of substitution around the world. And you can see in the last 10 to 15 years, this has stagnated at only around 20%. And this is due to the limitation on the availability of slag and fly ash. If we remove this limitation, which is very easy to do by the abundant availability of calcined clay, we can easily imagine to go to an average substitution level of, for example, 40%. On a world scale, this would represent a saving of 400 million tons of CO2 per year. And on a longer term horizon of 2050, I think we could easily go to a substitution of 55%, which would represent a saving of 800 million tons of CO2 per year. This is like 2% of the world emissions today. So this is a huge contribution from one single technology. On the financial side, we also have very good news because the calcined LC3 is generally cheaper to produce than the reference Portland cement. Even if you have to transport clay 200 kilometers from the plant, you can still save on your operating costs regarding OPC reference. And particularly good scenario is if you have a grinding plant in areas where you don't have limestone, so don't have good clinker production, you can really decrease your need to import clinker and get a very good material by using local clay. Now, this calculation we made a few years ago in 2019. Since then, the energy prices have increased enormously. And this increase in energy prices means that the financial situation of LC3 is even more attractive today. So I'm pleased to say that at present, we're now engaged with all these countries around the world, including China. And I think that, we really have a huge potential with this technology. These show you some examples of the plants which have been publicly announced around the world, in France, in the USA, in Ghana, in Colombia, in Angola. So you can really see that it's possible to produce this kind of material everywhere. Now, before I finish, I want to emphasize that LC3 is one solution that can be used in combination with others. And in this report we wrote for the European Climate Foundation, we calculated that if we combine the technologies we have, we can even reduce emissions by 80%. So on the level of the clinker, we can reduce the emissions of fossil fuels by using waste. On the level of the cement, we can use more supplementary cementitious materials like calcined clay. But we must also follow this through by reducing the cement in the concrete and then reducing the concrete in the buildings. And at all these levels, it has been demonstrated that it's possible to make very significant savings. For example, if we look at cement in concrete, we see that around the world there is tremendous dispersion. This concrete here uses 3 times as much cement as this one here. 3 times as much cement is 3 times as much CO2. So we can improve the efficiency of concrete by moving from site mixing to industrial production in ready-mix plants. This is an important technology in some parts of the world where much material is still mixed on site, but we really don't want to go in the reverse direction. And this is what is happening with the technologies like 3D printing, which are taking out the large aggregates. This increases the cement content and vastly increases CO2 emissions. So we really must be intelligent about solutions that can take us in the right direction of reducing CO2. And of course, if we want to make all these solutions work together, we really need to bring about a real revolution in the industry to get all the different sectors of the industry working together. And this is what has been launched with what is called the Globe Consensus. The Globe Consensus was coming from a conference in Tongji a few years ago. And now we have taken this forward. We have produced a policy document. But the main message of this policy document is that the different parts of the value chain need to work together. So we hope many of you will look more at this Globe Consensus. Here is the address, and really join this effort to lower CO2 emissions in the construction sector, which is really possible at very large scale. Before I finish, I just want to highlight a paper that will be published in Rylem Technical Letters very soon that I have written with my colleagues in Heidelberg Cement, Holcim, and Sika, where we look at all the different technologies and highlight their different potentials for CO2 reduction. So the ones here in dark green are the ones that have the highest potential to reduce CO2 on the time scale we're talking about, because it's no good having some wonder solution which is only available in 50 years' time. So to conclude, I hope I've managed to convince you that substantial reductions in CO2 associated with cement-based materials are possible. We must work at the cement level by increasing the substitution of SCMs. We must work at the concrete level by minimizing cement contents. And we must also work at the structural level, where systematically we see over-design on the level of about 20% or so, and therefore that represents another possible source of saving. All of these will actually lower cost, which is very good news. The remainder of CO2 we will have to deal with by technologies like carbon capture and storage, but these are very high cost and the infrastructure is not yet in place. On the levels of SEM, calcined clays are the only realistic option to increase this technology at a large scale. And the main advantage of this that it can be done today, it can be done fast, and it can be done on a very large scale. For any students who are listening, please consider coming to our doctoral school in February. And finally, I'd like to thank you very much for listening. You can find more information on LC3 on our website or following us in the social media. Thank you very much.
好的，谢谢 Scrivener 教授。那么我们接下来再有请回孟老师那个先由孟老师对这个刚刚你们都做的这个 LC3 水泥的这个专题进行一个讨论或者点评孟老师。
谢谢那个杨博士，也谢谢Karen 教授。那么应该说这个Karen 教授这个对这个 LC3 低碳水泥它的一个整体的一个介绍是非常的系统，然后既有研究的相关的一个应用成果，也有相关的一些的应用的介绍，以及对 LC3 水泥它的一个这个推广应用可行性的这样一些的这种分析。所以我觉得这一块这个东西应该说给我们是带来了一些给我们是带来了一些很多的一些的启发，特别是对这种新型的这种低碳胶泥材料。实际上我在这个Web of Science 上去专门查了一下这个我们 LC3 水泥中国的相关的一些的研究，我发现仅仅就是在这几年才有，而且只有8篇相关的文章。所以说这一块的这种低碳的这种新型的低碳水泥，在我们中国的这个研究应用还是有很长的一段的路要走。所以很感谢Karen 教授给我们带来这么一个详细的一个系统的一个这个报告。然后是这样子我能否再简单说2点一块的话呢，就是因为我们整个的一个中瑞的一个零碳建筑实际上是给我们开了一个很好的一个头，就大家去讨论这个零碳建筑材料相关的一些的这种话题。那实际上在我们这样一些的零碳或者低碳建筑材料的这个研究和应用的这个过程中间，我们发现一个的话呢，就是研究的确是很重要的，要推出这样一些的研发一些新型的这种低碳胶泥材料。但是与此同时，它的一个评价体系，它的标准建立，以及如何通过一些的政策的一些的这种鼓励它的一个推广的一些的应用，实际上这一块也是非常的一些关键的。特别是就是像我们这个零碳的建筑，就是做一些示范的工程，这个是对我们低碳的这个胶泥材料来研究和应用来说，这简直就是不可缺少的一环。所以说我觉得今天我们中建院那么通过这个零碳建筑这样一个主题来去讨论这个低碳胶泥材料的一些研究应用，我觉得也是非常的契合时机的这一块。然后第二点的话呢，我还想讲一下的话呢，就是因为我们国家现在是在大力的推进这样一个双碳目标的这个实现，特别是我们习总书记也是刚刚也说了，要大力推进我们的一个降碳减污的这个工作。那么降碳减污的话呢，我前面也说过，我们中国实际上铸建行业中间的碳排放量是占到了整个全部碳排放总量的51%的，所以铸建行业如何进行降碳的一个减污，它的这个任务是非常的重的。那么当前有很多一些的新的，除了低碳胶泥材料以外，还有新的一些碳捕集存储利用等等 CCUS 的相关一些的技术， 那么这些如何就是推动这些 CCUS 的技术在我们铸件行业中间去研究和应用，那这需要很多学科之间的一些的交叉的研究和很多人的一些的工作，才能够去推进整个我们国家这个双碳目标的一个顺利的一个实现。主持人，我主要就讲这2点，然后还是再次感谢 Karen 教授做的一个非常系统的这个研究的一个报告。
好的那么谢谢孟老师。那么我们其实那个观众也有一些问题啊，有一个观众问了，想了解一下现在低碳混凝土市场，混凝土水泥有市场化了吗？有哪些供应商可以生产？还是目前只是理论研究的实验阶段呢？这个请哪位教授回答？请那我们先请那个
Yes,
please.
so in many countries we have this already on the market. It has been used in France. It has been used in the United States. It has been used in Cuba. It has been used in Colombia. It has been used in Ivory Coast. So in all these countries, we have very good experiences. Holcim in France have even built several multi-story buildings from this and will launch production in 2 big plants next year. In the United States, it's already being produced by the company Ashgrove, and this has been used in several projects, like important road projects to look at different low-carbon cements. So we have many examples where it is really successfully used in the field.
实际上在中国也是一样的，是这样。那个杨博士，就是说那个我们很早以前就像这个水泥的话呢，实际上很早就有那种低温煅烧的这样一些的水泥的这样一些的研究，以及的话呢，像这个中国建筑材料研究院，他们也是大量推进了这种活性贝利特水泥等等相关的一些研究。所以这一块只不过呢是我们还没有把它就是归结为这个低碳胶凝材料的这个范畴。但是现在随着大家对这个低碳的这个重视实际上我们以前的很多的一些研究应用也是很有价值的。所以我的那个第一个结论上面就说的是，很多一些矿物质的利用是在现在来说还是就属于低碳胶凝材料一个很重要的一个部分。虽然我们现在还在不断研发新的一些的这种低碳型的胶凝材料，但是这种老的一些的这种方式方法仍然是对我们这个铸件行业的碳减排工作还是很有用处的，很有帮助的。
好的，好的。那么第二个问题呢是，水泥的碳减排数据是否进行了公开披露？从哪儿可以查阅到相关的数据信息呢？谢谢。
这个我这个 PPT 上有那个下面有附着这个相关的一些的报告，这种包括一些能碳报告，包括国内的，包括国外的相关的一些能碳报告，能耗报告，那么可以去查询这些方面的这些资料。这个还是有很多都是公开的一些数据，虽然就是说这些数据也不能说是100%准确，但是的话呢，毕竟是经过了很多的一些的系统的调研和分析以后，然后得到的相关的数据。
好的，谢谢孟教授。那么接下来一个问题呢，是想问 Scrivener 教授的，就这个水化产物和普通硅酸盐水泥有什么不同？这个叫做 hydration products。
Okay, this is an important point. And what is important about calcined clay cements is all the hydrates are the same things that are already present in other blended cements. So we can be very confident these will behave very well over the long term. We have somewhat different proportions. So in particular, we have formation of more what are called carboaluminate phases. This comes from the reaction between the limestone and the calcined clays. But these products are actually already present in existing cements containing limestone. So we know they will perform well on the very long term. And this is an important question because, you know, we have to have materials which will behave well over many decades. Some of the new materials being proposed have completely different hydrates, and we don't have the experience to know how these will behave in the long term. But with LC3, we have the same things that are present in the blended cements being used today.
好的，谢谢 Scrivener 教授。那么我们接下来一个问题呢是，相对于普通硅酸盐水泥和地聚物 LC3 水泥的缺点是什么？
Okay, well, I referred to one of the disadvantages, which is the workability, which may be higher. But I want to stress that this is really manageable because you can use the same admixtures that you use with normal cements. The other aspect about workability is that it's really not very different when you get to the concrete level. If you are looking in the laboratory on cement paste, you see quite a big difference, but this is not so much in the concrete. And as I illustrated, for some applications like self-compacting concrete, it can really be very good. The other thing which is talked about is carbonation rates. Now, we know that carbonation can sometimes cause corrosion of the steel. But again, here, it's important to emphasize that while the carbonation may be slightly higher than the reference Portland cement, it's really the same or better than other blended cements we're using today, because the carbonation rate is related to the clinker content. So when in China you have already very low clinker cements, you will not see any difference. And in fact, the LC3 blends may be better because the calcined clay is more reactive and therefore it causes a more dense microstructure. So these are really the things that have been talked about, but we think these are really manageable and are far outweighed by the advantages of lower CO2, a lower cost, and the widespread availability.
我简单补充一下那个地聚合物的一些的这种缺点啊，因为它这个地聚合物是通过碱激发的这样一个过程，然后实现它的一个交接的，所以它的话呢，相对来说碱度会比较高，可能会存在就是会加剧碱骨料反应的一些的风险，所以这个的话呢，的确是需要进行关注和重视的。
好的，谢谢两位老师。那么，接下来一个问题呢，也是想问 Scrivener 教授的，就是 LC3 的超塑化剂与普通硅酸盐水泥有什么样的区别？
All existing plasticizers work well with LC3. The best performance you will get from PCE type superplasticizers, and particularly when these superplasticizers have been designed especially for calcined clay, we see many producers of admixtures now have these specially designed superplasticizers, but all the superplasticizers will work.
Ah, 谢谢 Scrivener 教授。那么还有一个问题是，怎样鼓励以市场价格导向的建造商能考虑优先使用低碳水泥或混凝土？瑞士和中国各有什么样的政策和鼓励措施吗？那这可能得请两位老师同时回答一下。
Parent first.
Well, I think it's important, as I said, to realize that the production costs will be lower. You may need some incentives to favor the investment. And this is important when you're looking at the restructuring of the industry to move towards modern clinker production technologies. This means you will have many older cement kilns which become redundant, and these can easily be converted to calcined clays. I think this would be very good if the government could incentivize this. But also it's important to say that this technology is really compatible with other technologies which are being investigated. So, for example, I know that there is much work in China to use more waste materials as fuel, and this is a very good technology. But LC3 is completely compatible with this. So both can be done at the same time, and both these technologies will lower production costs. There may need to be some incentive for the investment in the calcination facilities.
OK， 在中国的话呢，实际上也有一些的针对这种低碳混凝土和低碳胶泥材料利用的一些的这种推进的一些措施。那比如说吧，就我们有一些绿建的一个绿色建筑的一个评价的一个标准啊，那么它也有相应的一些的推荐，包括推荐固体废弃物的一些的使用。但是的话呢，总的来说，就是说我们的这一块的政策体系的话呢，还是非常不健全的，还有助于更加的一些的细化，特别是呢是要有一些的大的一些的这种比较强有力的措施来推动我们这个低碳水泥和低碳混凝土的一个推广应用。
好的，谢谢两位老师。那么我们还有一个问题，就是今天Scrivener 教授的讲座主要是关于建筑材料方面的碳中和策略。那么这个策略 LC3 的策略会不会从建筑物的运营效率以及使用率方面来讨论碳中和的问题？比如说卡塔尔世界杯的8个新建体育场都采用了大量的碳中和的设计和建造策略，但是未来的使用率堪忧。这样一来，无论水泥和混凝土材料有多么环保，其在使用率上的性价比仍然会很低。为此，是否针对不同用途，比如说永久的建筑、临时的建筑，这些建筑不同的建筑材料的选择策略，否则建筑材料就算再环保，但是建筑只在赛时使用一次，赛后也会是巨大的浪费。不如采用可回收率高的材料，比如钢材、木材等。这个问题。
Well, I think, okay, I think, of course, we need to reduce the material usage, but we cannot replace concrete with other material. We will need concrete. And concrete is a completely recyclable material. Professor Meng really described this, that you can completely recycle concrete. So it's very wrong to think that only materials like steel can be recycled. No, this is completely not true. Concrete is a very good material for recycling and has much lower embodied energy in the first place than alternative materials like steel or bricks or things like that. So we need concrete moving forward. Of course, we need to reduce the amount we need. And this is why, as I said, we should really think about converting some of the facilities which are producing clinker to also producing calcined clay in order to be able to better optimize the CO2 of these materials, as well as decreasing the amount in the buildings by better design. All these technologies should work together. More waste fuels, using calcined clay, better design, all of these should work together.
Thank you for the answer, Professor Scrivener. Maybe I should have made my point more clear. So the point is not arguing between having concrete as construction material but I'm talking about the proportion of being recycled as a construction material. For example, for the stadiums in Qatar, even if we could demolish a concrete stadium, it will still take a lot of energy and a lot of time. However, if we can use other materials such as a prefabricated factory component like a steel truss, and then we then can disassemble the stadium very quickly. So it is about the development strategy for a permanent building or for temporary building. So my question
I think again, you are not really right, because you can make demountable buildings in concrete. There are now people making joints, and you can make concrete beams, which you can also dismantle in the same manner. But of course, you know, when you're looking at a temporary structure, then you have different considerations. But these temporary structures are a very small part of construction. The vast majority of construction are structures that are meant to be there for at least 50 years and maybe more like 100 years. So yes, in different situations, you can use different materials, but again, concrete can be recycled. It can also be constructed in a way where it can be disassembled and the parts reused. All of these technologies are already there.
我是沈林，是那个厦门大学的。
Yeah,
my name is Lin Shen. I'm a professor at University of Hawaii at Manoa. So I did some research on geopolymer concrete, alkali activated concrete, and had some experience on that. Very nice presentation, Professor Scrivener and Professor Meng. Just quick comments about Professor Meng's comments about geopolymer concrete on alkali activation, ASR, 坚固料反应. Based on our experience, the ASR potential is greatly reduced when we can optimize the alkali content and make it very resistant to ASR. Okay, yeah, just quick comments about that. Thank you.
Okay, thank you.
好的。那我们今天的分享论坛研讨会也接近了尾声。那么我们也是今天学习到了很多有关 LC3 低碳水泥的一些知识。那么从建筑全寿命期的角度讲呢，这种建材的低碳对于实现全寿命期的这个零碳建筑的目标是非常重要的。那么 LC3 水泥呢，在保证这个水泥性能同时呢，它能够显著的降低这个二氧化碳的排放以及这种成本。那么这种 LC3 水泥的这个对于中国市场来讲呢，我们还是需要更多进一步的研究以及更多的这个示范工程的应用。那么我们也是在此呢，非常感谢孟涛教授以及 Karen Scrivener 教授为大家带来的分享。那么也非常感谢今天的各位来宾，大家的讨论也是非常的充分啊。然后同时呢，我们也再一次感谢瑞发署、中国住建部、瑞士绿色建筑协会对本次研讨会的支持。那么有关这个中瑞零碳建筑合作项目的更多的一些信息呢，还是欢迎大家持续关注我们的公众号，并欢迎参加我们每月一次的这个中瑞零碳建筑系列研讨会。那么再次感谢大家。那么本次研讨会呢，现在结束，大家再见。
再见。
拜拜，孟老师。
Thank you.
拜拜。
Okay.
Professor Scrivener.